All right. This is just the continuation of Friday, I wish it was December, September the 27th. Okay, this is just the rest of the packet that we didn't get to in fourth period, so you can just kind of make sure we get all the answers. So what's the next step? So you weighed out the solid, then what's the next step? Sam, what'd you put as the next step?
I said you would add distilled water to the 200 milliliter volumetric flask, like about halfway.
Okay, and then what?
And then you would put the AgNO3 into it.
Okay.
With the scoop.
All right, you could scoop it in, or you can just kind of, did they even give you, they didn't give a funnel. So you can just scoop it in. Now, the order on that one doesn't matter. You can probably put the solid in first and then add the water, okay? But you just transfer with the scoop, okay? With weighing paper, transfer it in, add about half full, then what?
After it's like dissolved.
Swirl to dissolve, okay? Swirl to dissolve, then you add water. How much more water?
So it reaches the 200 milliliters.
Until it reaches the line. Now, is there another step that technically we should do? I would, put a cap on it and invert it to make sure it mixes completely. But it doesn't give you a cap, okay? But, and you might want to say then swirl to ensure, but I might even just add in cover and invert just to ensure complete mixture. But that's always gonna be it. You weigh it, you use the volumetric flask. A pipette, just for the record, would be used to transfer a specific volume. If you needed 10 milliliters or 25 milliliters of a solution, and you were gonna maybe dilute it to 200 milliliters, and you wanted to get an exact volume, you could use a pipette.
Could you use it if you were like at your
Okay, this is a pipette. Okay, this is a 10 milliliter pipette. It's designed, it's got a line on it. It's a volumetric pipette. So again, if you want to transfer a very specific amount of liquid, you use a pipette, and then you have a little rubber bulb that you put on here to suck. You don't just suck it up like a straw. You use a pipette bulb and suck it up and get it to the line, and then that allows you to transfer a volume. You would not use a pipette for solid. You're going to use the scoop, just like Sam said. Okay. Now there is also this right here is called a graduated pipette. It's got lines all on it, so you could use this as well to deliver varying amounts of a liquid.
So you could use it to add, like, to get it to the 200 milliliter line?
I mean, we usually use a dropper or something on that, but this is designed just to deliver. You can pick up 5.5 milliliters of a solution and then transfer it to somewhere else.
So would I want to put that down or not?
No. No, I'm just showing you other ways that, because pipette is listed, when would you use the pipette? You're never going to use a beaker to measure. That's the least accurate way to measure anything. Okay? And I don't know if you said fill it up with distilled water, if you use the word distilled, okay? But you want to fill it up, use the distilled water on that, okay? All right, so we practiced, we've made our solutions, we did the Beer's Law. Hey, by the way, Beer's Law is part of the test on Monday, okay? And I gave you, your Beer's Law labs back, okay? All right. Let's just look at these last few. This is a particulate drawing, okay? See, what do you think, but given the balanced equation above, okay, what would the right beaker look like? balance team. All right, so what do we get? We're still working? For every one AL that reacts, how many Ag pluses are gonna get reduced?
3.
3, okay? So how many aluminums actually react? 2, correct? Okay, we got 2 over here. We had 4 to start with, so 2 reacted. So I'm gonna have 2 Al3 pluses. Okay, so how many, does that mean how many Ag pluses got reduced? 6. 1, 2, 3, 4, 5, 6, but I got 8. So that means that I'm gonna have Ag, Ag 2, 3, 4, 5, doesn't matter where you put it, 6. And what's gonna be left? Well, actually,
Wait, aren't they solid?
they're solid. Those are all gonna be solid, so they're all gonna be down here at the bottom. 1, 2, 3, 4, 5, 6, Ag. Okay? Shown on the left, and be sure to include the correct type and number of particles based on the number shown on the left and the relative spacing to depict. So they're all just gonna be right next to one another as a solid. Okay? Now what else is gonna be in there?
2.
2 Ag pluses.
Excess.
Okay, just floating around. Okay? So, the solid's gonna go to the bottom. The ion's just gonna be there, but it's just, I mean, you just simply count and use the balanced equation. That should be an easy money question. Okay? That might even be a 2-pointer. All right. Last page. Oh, go back to a solution problem. Okay, now A, I'm not sure how much easier A can get, okay? You have 0.0016 grams over 1 liter. How much do you have? What are they asking for?
Moles.
And how much? 1 liter. So it's gonna be times 1 liter, which you don't really have to do. So that means you got 0.0016 grams. Well, how do I figure out how many moles there are? Molar mass, which they give to you. So you're gonna say 1 mole over 51.48 grams, and to 2 sig figs, what's that gonna get me?
4 zeros and 3 1.
4 zeros and
3 1.
1, 2, 3, 4, 3, 1 moles of NH2Cl. Okay? I mean, easy money. Okay, Justin, what are you looking at so strange for?
9.
Did you have it set up the same way, you just got a different number? Okay, it's just 1 liter, so it's this many grams per liter, so you know that you have that many grams, just divided by the molar mass. Okay, now, this one's kind of crazy, in that it says NCl3 is nearly insoluble, but it's got nitrogen and chlorine in it. But if it's insoluble, what does that probably mean about its polarity?
Non-polar.
It's probably nonpolar. Well, why wouldn't NCl3 be nonpolar? Because they're phone call.
They're all phone.
They're all phone calls. So they're all strong, so they're equally strong. Nitrogen and chlorine are very close to one another in terms of electronegativity. Our periodic table says nitrogen's 3.04, chlorine's 3.16, but most books put chlorine and nitrogen both at 3.0. The same electronegativity. So, but we can just assume, since it says that it's nonpolar, that it's insoluble, that it has to be nonpolar. So, and it's highly soluble. This is understandable because it's asymmetrical. You got a nitrogen and a chlorine, and you got the nitrogen and hydrogens right there. So this is polar, okay? Explain that in terms of the types and relative strengths. So what types of intermolecular forces are there going to be in NH2Cl? LDFs, dipole-dipole, and hydrogen bonds. Because it has the ability to form strong hydrogen bonds with water, NH2Cl is very soluble. However, the NCl3 will only form what? What's the only type of attraction between it and water? Dipole-induced dipole, which are too weak to overcome the much stronger hydrogen bonds between water molecules. As a result, water doesn't separate and the two are insoluble. Okay? Now, I wanted just to kind of, that's the same thing that we've been talking about for 2 days now. It's just this one's weird because it has phone call in it. We just need to know that it's symmetrical. Well, it's not really symmetrical, but they're even. I can do this. They have the same electronegativities. All right, we have 15 minutes for me to show you how to do the bonus. Okay? But first off, here's your study guide. This is everything that we've been talking about. Lattice energy, energy of hydration, delta H1 plus delta H3, your sign, your exothermic, endothermic and strong lattice energy, exothermic energy of hydration. This is everything that we've been talking about lately. You got to know your strong acids and strong bases. Net ionic equations, just like one of them on there, okay? It's just being able to do your net ionic equations. The effect of temperature, delta, all that, okay? So that's all the things that we've been talking about, okay? Pressure has no effect, molarity problems, dilution problems, and then the stoichiometry. Okay, so this is just kind of the gist of everything we need to know. But here's your bonus. Okay, here's the bonus. So I'm going to show you how to do the bonus in 15 minutes. And this sheet that I'm going to use as an example, I haven't posted it yet, but I'm going to post it online. We have 3 other ways of measuring concentration other than molarity. We have, obviously, molarity, capital M, is equal to what over what?
Moles or liters.
Moles of solute over liters of solution. But then we have molality, which is a little italicized M, which is going to be moles of solute, anybody remember, over, it's going to be kilograms of solvent. Now, all of these equations are given on your equation sheet that you will have on the test, okay? Just so you know, you don't have to memorize the equation. We have a third one, where it's percent by mass, which is going to be the mass of the solute over the mass of the solution, and then times 100. And then if you want ppm, I don't know if you've ever heard of a concentration given in parts per million. Have any of y'all ever heard of that, ppm? I mean, it's something that when things are really dilute, that they have to give it in terms of parts per million. It's simply going to be times 1,000,000. It's the exact same, except it's times 1,000,000 instead of times 100. Okay? So you still do mass of solute over the mass of solution, but rather than multiply by 100, you multiply by 1,000,000 ppms. And then this is 1, 2, 3, and then 4 is mole fraction, which for some reason or other they use X, which is going to be moles of solute over total moles. And total moles is going to be moles of solute plus moles of solvent. All right, so these are the 4 different ways we can measure. We just have to be able to go between these 4. Okay, obviously moles to moles, but the difference is liters of solution versus kilograms of solvent. So we always have to keep track and know that a solution is solute plus solvent goes to solution. We have to differentiate between those. All right, so if I look at a problem like $25 will be a good one. I need a blank piece of paper. 25. A 1.37 molar solution of citric acid in water has a density of 1.1. This is the key. This is the one thing that you have to know in order to be able to go between. You have to have that additional information to be able to go between these, because that's how we're going to get from liters to grams, is with density. Okay? So, a 1.37 molar solution equals 1.37 moles of, and I'm just going to say citric acid, over how much? one what?
Liter.
1 liter of what? Solvent or solution?
Solvent.
Solution.
Solution. So that's going to be the key here. We have to know that it's that. Okay? So then it says calculate the mass percent, the molality, and the mole fraction of the citric acid. So I know how many moles of citric acid I have. Is there any way for me to get the grams of citric acid? Use the molar mass. So I can, let's just say that this is going to be A, B, and C. Okay? So A, I want to get the mass of everything. This is the hardest part. Once you get this one thing, the rest it all just falls into place. So 1.37 moles of citric acid times the molar mass. Now the citric acid is given as H3C6H5O7. H3C6H5O7. So I just got to get the molar mass. So I'm going to say, okay, it's 12 times 6 is 72, plus 8 makes 80. 16 times 7 is equal to 112. 112 and 80 is 192 grams per mole. Okay? 192 grams over 1 mole. So somebody get that value for me.
$263.04.
263.04. We'll just say 263 grams of citric acid. Okay? But I need the mass of the solution. Well, how can I get from liters of solution to grams of solution?
Density.
That's where the density comes into play. So I can say that I have 1 liter times 1.1, well, it's cubic centimeters, so what do I need to make that?
Milliliter?
How many milliliters is it going to be?
Isn't it equal?
1,000.
No, it's 1 milliliter equals 1 cubic centimeter. Okay, so a liter is going to be 1,000 cubic centimeters times 1.10 grams over 1 cubic centimeter, which means that I have 1,100 grams of solution. Okay? I use the density. Now, what's my mass percent going to be then? 263 over 1,100 times 100 Say it again.
23.9.
23.9%. Now, if I multiplied that by 1,000,000, I would end up getting my parts per million. Now, this is way too concentrated to ever want to use ppm, because that'd be a huge number. Most of the time, it's when it's very dilute, and you need to get numbers a little bit bigger. Okay, but now we have really all the information that we need to do everything else. So B, we want to get the molality. Well, the molality is moles of solute. Well, do we know moles of solute? How many is that?
1.37.
1.37. It's the same as molarity. But I need kilograms of solvent. Well, I can say that the molality is equal to 1.37 moles divided by, how do I get the kilograms of solvent? Well, solvent. What's it going to equal? Well, the solution is solute plus solvent. What two things do I know?
Solution, solid.
I know the mass of the solution, 1,100, and I know the mass of the solute, 263. So the solvent is gonna equal solution minus solute, which is going to equal 1100 minus 263, which is going to equal 837 grams, which is how many kilograms? 0.837. So then I can just plug that in here, 0.837 kilograms, and my molality is going to equal anyone? 1.64 molal. And then lastly, C is the mole fraction. Well, I already know that's X of citric acid. The X is 1.37 moles, and it's going to be a 1.37 moles plus the moles of solvent. Well, how do I find moles of solvent? What's the solvent? What's the solvent here? Water. Do we know how much water there is? 837 grams, right? So I can say the moles of water is going to equal 837 grams times 1 mole. We've all memorized 18.02 grams. .45 moles of water. So that's just going to go here, 46.45 moles. So you just add those two together. It's not times 100, it's just a fraction. So it's got to come out to a decimal, 3 sig figs.
0.0286.
0.0286, and there are no units on it. Because it's a moles divided by moles. So to be able to go between them, you just have to figure out solute. Now, there's a bunch of different ways. Okay, they give you molality, and you have to go to molarity. They give you molarity, you have to go to molality. But it's the density is how we go back and forth between kilograms and liters. And then you just have to separate your solute and the solvent from one another. Now this is 100% bonus, okay? It's not on the AP test, but it is something you do in college. Go Jags.